screen now?
Yeah, we see. Okay.
Okay, so apologies if I have background noise, and I will see how we go on this. So my talk is about making recycled PET and polypropylene acceptable for food grade applications. And this is really a topic which is quite a complex topic, but we will try and fit in the key concepts in a short presentation. So just to say a little bit about Nextek and what we do, we design recycling factories, we design technologies to help recycle post-consumer plastics, and we advise companies about how to use recycled plastics back into new packaging applications. Some of the work we've done has been given awards. We've recently won the World Star Award for our Next Loop project for recycling polypropylene back to food grade. But let me start by saying that there are two major regimes for food grade regulations. So they are both the European food grade regulations and the US FDA regulations. And if we just focus a little bit on the European ones, the reference regulation is EC 282, 2008. And this has a number of important points in it. And it is a control mechanism to make sure that recycled plastics are pure. And I'll go into that in a moment. And the first thing is only food grade materials can go into the recycling process. So they have to be compliant with the regulation 10/2011, which means all of the ingredients have previously been approved for food grade in the polymer. And then there must be a migration test, which is carried out by first conducting a challenge test to make sure that no harmful chemicals can migrate into foods. And the regulation there is 1935/2004, which regulates that packaging must not change the nature or flavor or the taste of food. In the US, the regulations are similar but different. And so here, they look at migrating substances as food additives. So if anything migrates from the package into food, it's considered to be an additive. And then the toxicity of that additive is assessed. So they do also have, importantly, a threshold of regulation. And this means that there is a level below which exposure to a potential toxic substance is negligible risk. And they put that level as 0.5 parts per billion in the daily diet. Now, and so when you develop a recycling process, you must demonstrate that you can get to levels below that 0.5 ppb migrating from the package into the food. So those two regimes are similar but different. And EFSA is probably the one that's more stringent, purely because it has more regulations around it. And they have set a concept where they say that there must be very low levels of potentially genotoxic materials migrating from the package into food. And so they have set a limit of 0.2225 micrograms per kilo of body weight per day. So that means for an adult that in the food, there must be less than 0.75 micrograms per kilo in the food. And in their modeling, they not only use the adult, but they also used an infant or a toddler. So the weights are 5 kilo or 12 kilo for a toddler or 60 kilos for an adult. In their considerations, they say that no more than 5% of the materials can come from non-food applications. In other words, it has to be at least 95% food packaging in the recycling stream. And non-food containers should not intentionally be used. This is quite important. And the resins that are used in the recycling process must meet the approvals of both the EU regulations or USA. If not, then they must be proved that they meet those regulations. And then they also specify a challenge test, which has to be real scale and the process conditions have to be maintained within the factory to specific standards. So here is a graphic about how the two things work. And on the right-hand side of this graph, I'll see if I can get my cursor to work here. On this side, what they do is they create a challenge test where they intentionally contaminate a plastic, and then they decontaminate it through the recycling process. Now, so you put in contaminants at a high level, let's say 1,000 parts per million, you decontaminate, and the level drops to a lower value. And so that gives you the cleaning efficiency of the recycling process. And on the other hand, what they do is they look at the migration modeling for materials. So on the right-hand side, you can see we have the level of 0.2025 micrograms per kilo body weight, which means, let's say, for infants and toddlers and adults, that gives you the concentration in the food that's permissible. So then they do a calculation of how much can be allowed to be in the bottle, and using migration modeling would result in this level of migration into the food. So you have two sets of results. You have a calculation which is based on the residue that might be occurring, and for PET they make the assumption that there is 3 milligrams per kilogram of genotoxic material present in a bottle due to misuse applications. And so once you apply the cleaning efficiency, you can get your residue concentration of the residues. Now, if your residues are less than the modeling results, that means you will have a lower concentration based on the decontamination process. So it'll be lower than the modeled concentration. And this way, they will define the process as being safe. So this concept is what Fs are used for PET and also for polypropylene and high-density polyethylene. And what it means is this decontamination efficiency is a key factor in determining whether a recycling process is efficient enough to make it food safe. And so you can see that for, in this graph here, we have the minimum cleaning efficiency for bottle for infants. The cleaning efficiency has to be very high as a function of molecular weight. But for adults, we can have a lower decontamination efficiency because the body weight's higher, so the concentrations allowed are higher. But the important point is you ideally would have very high decontamination efficiencies in the 90% plus. And this also, there's another important point here is what is the background contamination level of the material that is normally found in post-consumer PET or polypropylene or HDPE. And I'm going to give the example of HDPE in a moment as well. And in some cases, they have a specification of either 95% food, non-food food packaging, or in the case of polyolefins, the specification is 99% food packaging. And so these are very important targets to remember. So here's an example of the decontamination efficiency for a PET process. And you will be able to see in the first circle, I've got here, we have the concentration of contaminants that have been put intentionally into a test material. And then after decontamination, you can see in the next column, you can see that the levels are much lower. And then this is how you calculate your decontamination efficiency. So all these results, this is based on a vacuum prime system with 3 reactors. The decontamination efficiencies are greater than 99% for most of them, down to 98% for Lindane. And so what this means is you can now do the calculation if you have 3 milligrams of genotoxic material, you can apply the decontamination efficiency, and then you can calculate the residual level of materials in the finished product. And of course, you can compare them against the modeled residues. And so you can see that the materials that are based on decontamination are lower than the modeling, which means this material would be safe. Now, in the case of HDPE, we have the same sort of approach. The recycling process that's used currently in the United Kingdom for HDPE uses 2 reactors, not 3. And in this case, the reactors are under vacuum and elevated temperature, typically 120, and it's kept under vacuum for 2 hours. And the materials are processed. Now, when this work was done, I will just come back to this here. You can see here the concentrations at the start. They're all typically close to 1000 ppm. And then after the cleaning step, the decontamination efficiencies are in the 99% for the solvents, and for the middle molecular weights, they are lower. And you can see that in some cases, for benzophenone, for example, it's 11%. But if you put 2 steps in, it increases. So you can see that for benzophenone, the decontamination efficiency is low. And this process for food grade HDPE qualifies for US FDA, but it does not at the moment qualify for EFSA. So this is one of the points of difference between EFSA and US FDA. And when a study was done on misuse for milk bottles, it was shown that after many inspections of bottles carried out to determine was there misuse of milk bottles, and these are plastic high-density polyethylene bottles, it was found that essentially there was almost no bottles that were misused. For example, they weren't used for storing other chemicals or other solvents or other materials. And so we can say that misuse in high-density polyethylene is extremely low. However, the use of non-food bottles, for example, in HDPE for detergents and so on, these materials can always creep into the process. So that has to be taken into account. I'll say a few words about polypropylene recycling, because this is the area that is probably missing from food grade recycling up till now. And we started a project called Next Loop, which is all about closing the loop on polypropylene. We have quite a big group involved in this, 38 members working on this project. It has 2 technologies, one called Prism, which is the sorting technology to sort food from non-food. And then we have Pristine, which is the technology for decontamination. So these 2 are worked together to give the full process called Next Loop. So the way it works, we have for the sorting, we have labels on the packaging with a fluorescent surface. So under ultraviolet light, the illumination makes the label appear a specific color. So here's an example of labels in daylight and under ultraviolet light. So if we illuminate a package with a fluorescent label, the machine will actually see a colored label. And so this is what the sorting machine sees. Normally these labels are they're white with no color, but under ultraviolet light, the machine can actually see the colors, and we can see the wavelengths of the colors, and we can register these for ejection. And in a recent trial, we've taken something like 50 different packages and put fluorescent markers on them, and we've conducted sorting trials on them. I'll show you a short video of this happening. So in this video, you will see packages that have the fluorescent label, and they are being put through a machine, and you will see the sorting system. The sorting system will illuminate the labels. You can see the pale blue line across the belt. And once the bottle is illuminated, it will be identified and it will be ejected. And you can see the automatic ejection, separating the food from the non-food materials. So this is where we end up with the separation, and the average purity of the sorted packs in the first pass is 99.3%. That's our average separation process. Sorry, we'll just go past that. Here we go. So if we look at the sorting, this is by different brand owners. Many of the packs were sorted with 100% purity in one pass, and we can take a second pass to boost the purity to greater than 99.9%. So the capacity to sort is a readily available function. So, and here is an example of a factory where we retrofitted the sorting system to a factory in less than 1 hour by adding ultraviolet light and then putting the packaging through the system. It's very simple to do. We just have to change the label. Now, the other half of the recycling technology is the decontamination process, where we do it in 2 stages. We do it by melt decontamination and solid state decontamination. And here you can see we've got 6 different surrogate chemicals, and those surrogate contaminants are put in at approximately 1,000 parts per million and then decontaminated. And the decontamination rates are of the order of 100% for the solvents, 99 for the middle molecular weights, and about 98 and 95 for the middle molecular weights. So this gives us very powerful decontamination performance. And for polypropylene, the initial contamination level is extremely low. So we know we can eventually end up making food grade materials. When we test the migration behavior of the materials afterwards in contact with different solvents, so this one is 10% ethanol for 10 days at 20 degrees C, we basically had no migration into the ethanol. So the limit of detection was of the order of 4 to 5 parts per billion, and we were getting no migration at those levels. So we know that these materials are completely decontaminated by the process. This allows us to be confident, and we've had legal opinion that the process meets both US FDA and EFSA food contact regulations. And here's some examples of some of the food grade materials we've made. We've made many more, but I was meant to keep this talk to 20 minutes. So that's all we got time to show. So in summary, there are strategies for making food grade recycled materials. They have some very important stringent conditions associated with them. So, so EFSA at US FDA outlined these materials, these steps. And of course, the food grade HDPE has been used for over 14 years without any problems. So the US FDA assessment is probably correct that it is safe. EFSA are still equivocating on their judgment. And now the next loop process is being developed for both EFSA and FDA. That will happen in 2022. And as we were saying earlier, the key point here is to have complete separation of food from non-food, which requires the use of these fluorescent markers. One point to mention, the challenge tests that are being used for PET need to be modified for the polyolefins. That's a very important topic, but I'll just make the statement that we must not use the same test that has been used for PET for polyolefins, because you get distortion effects. And of course, we expect more work to happen on polyolefins, because as our first speaker very correctly said, the biggest volume packaging materials are indeed polyolefins, and PET comes later. But actually PET is easier to recycle than polyolefins. And so that's my last comment. So thank you very much. And I hope we can come back to some questions a bit later on. Thank you very much.